Good morning, everybody. I hope you're not hungry. Last talk before lunch. At the outset, I want to thank Dr. Pankaj Agarwal and Dr. Sunita Agarwal for having me here and for being such great hosts. My first visit to Bangalore, and so far I'm really loving it. So moving on from regular stem cells to cancer stem cells, and this is something I'm sharing with you part of the work. So if I can go to the next slide, please. So this is the way I've planned to lay out my talk. Was a little bit about cancer, then the cancer stem cells, and two different strategies by which we have tried to target cancer stem cells. The first is we've targeted cancer stem cells from cervical cancer. That is the work which has been done not from my group, but from Dr. B.C. Das's group, who is the chairman of the AMITY Center for Stem Cell Research, AMITY Center for Institute for Molecular Medicine and Stem Cell Research. Basically work done by one of his PhD students, Abhishek. And can you go back just a little bit? And the second part of the talk is looking at glioblastoma multiforme, grade 4 glioma, a brain cancer, pretty deadly cancer, work done by one of my postdocs when I was working at Cleveland Clinic a long time ago. Why I want to highlight these two, because two different approaches trying to target cancer stem cells. So cancer, as you all know, is probably a pretty deadly disease, one of the leading causes for morbidity and mortality, and we are expected, we want to, but we project that there is going to be a dramatic increase in the number of cancer cases and also in the number of cancer-related cancer deaths, despite so much of efforts that we are making to treat cancer. So two things very, very important for handling cancer. One is, if we can catch cancer early, we can handle it. And another thing is that most of the therapies that conventionally we've been using are not targeted. So patients will not die because of cancer, but patients normally die because of the side effects for the therapies. So if we can have targeted therapies, then we can treat cancer better. Cancer can occur because of natural reasons, what we call nature or nurture, because of inheritance or specific disease. We know about the BRCA1 and the BRCA2 cases made more popular by Angela Jolie, getting her breast removed because of the mutations, or due to exposure to radiations or chemotherapy, viruses, and you have the chronic gastric reflux, which can later on lead to gastric cancer. And you have basically clonal proliferation, starts from a single cell. There are a multi-step model for carcinogenesis evolution, and you have a pre-malignant state which leads to malignant state because of serial accumulation of mutations, leading to clonal evolution and resistance. Two different models for cancer development. One was the traditional model, the stochastic model, and what it really proposes is that any cell of the tumor has an equal ability to form tumors. So any cell has that probability to develop into a full-blown tumor. However, the hierarchy model, or what we now know as the cancer stem cell model, is that it's a small proportion of that tumor cell which has the capability to maintain that tumor. And this hypothesis says that if you eliminate bulk of the tumor, but you are not able to remove the what we call the neoplastic clones that maintain the cancer, the tumor will come back. And if you want to really handle cancer better, we have to target these what we call the tumor initiating cells. And they have been characterized and in different kinds of cancers, both solid tumors and liquid malignancies. We have been able to identify different proportions of so-called cancer stem cells. And they are characterized by either specific cell surface markers and formation of spheroids. So if it is brain tumors, we call it neurospheres. If it is breast cancer cells, we call it mammospheres, and so on and so forth. But another interesting characteristic is that they have what we call an active ABC transporter, which will pump the drug out. So they have an active drug efflux mechanism, and these are some of the ways by which we characterize. These are some of the cell surface markers for different cancers. And like I said, that as per the stochastic model, you want to remove the bulk of the tumor, wanting to treat the cancer, but if you are not able to handle the cancer stem cells, it comes back and becomes deadly. So you have to target the cancer stem cells which are really propagating the cancer. Conventional therapy, surgery, radiation, chemotherapy, or a combination of any of these. But these are some, like, you have the cancer hallmarks, so these are the cancer stem cell hallmarks. I'm not going to go into the details, but I want to point out here that these cancer stem cells have an inherent ability to survive chemotherapy or radiotherapy. And that is probably why when the cancer is relapsed, what really happening is that you have a higher proportion of cancer stem cells. And another thing that people have been working on is that actually the lower doses of chemotherapy or radiation therapy in terms of targeting cancer stem cells actually works as a mitogenic signal or as a signal for these cells to start proliferating. So normally cancer stem cells sit quietly and contribute to the development of the rest of the tumor, but what really happens is that if you expose patients to either chemotherapy or radiotherapy, which is actually enough to target the normal cancer cells, but because the cancer stem cells will have a little bit higher tolerance to these drugs or to the radiation levels, it works as a mitogenic signal, what we say, induces mitosis, induces cell proliferation. And that is why you see that when there is a cancer relapse, it is more aggressive and more difficult to control. Okay, next slide, please. So, coming to the first example where Abhishek tried to look at cervical cancer stem cells, and this is just a flow diagram, how he tried to identify the cancer stem cells from the cervix, looking at CD133 and looking at the site population, and he's trying to use the mechanism of the ABC transporter being highly expressed in these cells, okay? Next slide, please. I'm not going to go into the details, and this is just to show we took different kinds of cells, two cells which are HPV positive, because we know that cervical cancer is driven by HPV infection or infection with human papilloma virus, and if you vaccinate individuals with HPV vaccines which are commercially available in the market, the chances of you getting cervical cancer dramatically reduces. So this is just, you have two cells which are HPV positive, which will express pretty high levels of the transporter, looking at flow cytometry, and the cell which does not express, is not HPV positive, does not express this transporter. You can see that on the flow cytometry, you can see it on the RNA level, and you can see it also on the Western blot at the protein level. Next slide, please. And what he actually also was able to demonstrate that these cervical cancer stem cells isolated or purified based on the site population, based on the expression of the ABC transporter, expressed higher levels of the HPV derived oncogenes, which is very well established. This is nothing new. That, okay, you know, how the human papilloma virus causes cervical cancer is by transfer of the E6 and the E7 oncogenes from the virus, which has to be integrated into the human genome for the cancer to actually develop. So before that, if the virus exists in an episomal fashion or these genes are outside the genome, then you have what we call a chronic HPV infection, but it is a pre-cancerous situation. So for a transformation of a pre-cancerous stage to a cancerous stage, the overexpression of these virus-derived oncogenes is important. And what Abhishek was able to show was that in the cancer stem cells, the expression of these E6 and E7 genes was very, very high. He took these cells, put them in the neat mouse, and on the two sides, the left side and the right side, on one side he put the cancer stem cells, the other side he put the non-cancer stem cells, and you can see a great difference in the tumor weight and the tumor volume. Next slide, please. And very, very interestingly, what he did was he compared the histology of the tumors that was formed in these mice from these cells and compared it to the primary cervical tumors derived from human patients to look at if there is any difference in the kind of tumors being formed and how closely this model is reflecting what is actually happening in the human patients. And the pathology looks very, very similar. Next slide. And actually, then we went and he went one more step ahead. He did, and the data I'm not showing, the data is in the next paper. What he showed was that he took the primary tumors from the human patients, isolated the cancer stem cells in a very similar fashion what he did from the cell lines, and then put them in the mice and then compared the pathology or the histopath. And very, very similar. So what we were seeing in the cell lines was also could be replicated using primary cells. So this is the summary for his earlier part of work. But the next part is what is the mechanism. So what Dr. Das's lab had earlier established is the role of AP1, which is a family of transcription factors, which is important for transcription of the human papilloma virus genome. So what the question that Abhishek started to ask was, do these cervical cancer stem cells show radioresistance? So basically trying to ask whether they are recapitulating what exactly the hypothesis is that they are radioresistant. Does it relate to the status of the different members of the AP1 family, and how can we target these cells? So this was something that he showed in a paper came out earlier, I think in March this year. He could show the change in the expression of the different members of the AP1 transcription family members. Next slide. And if you expose these cells to UV radiation, there is a further change in the expression level of these transcription factors as seen by immunofluorescence. And you could also see a change in the formation of the neurospheres. You don't see that. And if you treat them with curcumin, which is a known drug, you can disrupt that, and curcumin actually radiosensitizes these cells. So if you expose these cells to UV, there is not much of a response, but if you pre-treat these with curcumin, you have radiosensitization and changes. We can see both at the Western blot, and the data is not shown is what we can see even at the RNA level. So this is something, a model that we developed, that curcumin where, what does curcumin do? So this is a work which was initially modeled by Seema Bhatnagar, one of my colleagues, along with Abhishek, to show what is the possible mechanism of curcumin targeting these cancer stem cells. So it really sits in the pocket of the ABC transporter. Next slide, please. So what Seema is now going ahead along with Dr. Das is trying to develop a triple conjugate where we are trying to use a conventional drug which works on cancer cells but cannot be used because of its high toxicity levels. We are conjugating it to curcumin, and we are also conjugating it to a folate receptor which specifically targets cancer stem cells, because there is a differential expression of folate on the cancer cells and the cancer stem cells, and there are preliminary results, very preliminary results, so I'm not sharing with you, that it really is working and we can specifically target cancer stem cells, and we hope that once we are able to take it to the mouse models, we are very hopeful that we will get some good positive results. So that is the story for cervical cancer. Next slide, please. This is something that, so where we are targeting cancer stem cells by using some properties. Here we are using something slightly different and actually would be very similar to what Sunita had just talked about, differentiation mechanisms. I'm looking at it from a different perspective, okay? So we were trying to induce differentiation of GBM cancer stem cells, and the idea is very, very simple. Idea is that most of the cancer stem cells are undifferentiated in mechanism. When you treat a cancer, you are able to target most of the cancer cells, but the cancer stem cells you are not able to target. So if you can induce these cells to differentiate into whatever lineage, then we can target them as normal cancer cells because they are differentiated, they are no longer stem cells. So that was the concept. So, and starting from identification of the brain tumor stem cells, done by Singh and his group long time ago at Vancouver, where they identified CD133 as a marker for brain tumor stem cells. But we had a problem with this. So I put one of my PhD students, Taputi, looking at expression of CD133, and she found this very interesting thing that like, what you have is you have a U87 cell line, a GBM cell line, you have a U251 GBM cell line, and you have 4 different lines derived from primary tumor. So you see the CCF numbers, Cleveland Clinic Foundation numbers. Expression level of CD133 is very variable, but all of them form neurospheres. Okay, next slide, please. And we find that U87 cells having almost no expression of CD133 forms these very nice tumors in mice. Meaning to say that they have this in vivo tumorigenicity. Next slide. So we wanted to explain, and we went back to literature and we saw that what is really required for GBM formation in the mouse model. So if you take the neural stem cells, you put in RAS and you put in AKT, you can form tumors, and you can inhibit GFAP expression, like GFA is a glial fibrillary acid protein, which is a marker for glial differentiation. And what if you take differentiated astrocytes, you need MYC along with RAS and AKT to do the same job. Next slide. So we went ahead and looked at the MYC expression. The U87 cells express MYC pretty well, and the other cell line does not form it. We looked at GFAP expression. We found that U87 cells express pretty low levels of this differentiation protein compared to U251, which does, and you can see that whether you put them in the flank or you put them in the brain, U87 has very good potential to form tumors in mice or rats in vivo models. Looked at GFAP expression as expected. The cells which have good tumorigenicity express low amounts of GFAP and high amounts of nestin, which is a marker associated with stem cells. So look at the mechanism. We started to look at how these genes may be regulated. So we got this construct, GFAP promoter construct from Abhijit Goa from the Sick Children's Hospital at Toronto, and the nestin enhancer we cloned ourselves, put it upstream of the minimal TK promoter and put it in a luciferase construct so where you could measure promoter activity. We found that GFAP is very well expressed. The promoter is active in the U251 cells, while the nestin enhancer is active in the U87 cells. Remember, the U87 cells are the ones which form the tumors, and the U251s which do not. So there were reports, and I'm not going to go into the background why we started with P300, because there's a lot of background there. It's a long story. So P300 we overexpressed, and it promotes differentiation. As you can see, it promotes GFAP promoter activity and inhibits nestin. Next slide. It binds to the GFAP promoter and to drive that, and it is dependent on STAT3. And why we interested in STAT3 is a long story. Our lab had been working on the role of STAT3 in GBM for quite some time. I think this is a paper published in 2010, and we started working on STAT3 in GBMs probably in 2000. Okay, so that's a long story, but another thing. So we stably suppress P300. We can reverse the effect of the overexpression studies. Next slide. And we can see that in the immunofluorescence. And it's not only that, we can see that you see increased invasiveness of the cells where you have knocked down P300. This is Srijit's work. So we knock down P300 using RNAi, and we can increase invasiveness, which is quantifiable. Next slide, please. And also changes in the in vitro migration, as you can see in a scratch assay. Next slide. And what we did was we overexpressed MYC on the other side, and we used the MYC suppression by using shRNA. We got the effects. What was just the opposite of P300. But we were really interested in that. What is the correlation? Who comes first? So we did MYC overexpression along with P300, and MYC can override the next slide, please. MYC can override the P300 effect. So MYC is the primary driver, and that is not very surprising because MYC is one of the 4 Yamanaka factors which induce stemness, so which is known. So that is not very surprising. Next slide. So this is the same thing. Next slide. So what we have actually shown is that actually you can modulate differentiation of the cells or the so-called cancer stem cells. And the whole idea of doing it is that can we now use it as a screening mechanism to look at molecules which can promote astrocyte differentiation? Because obviously, like, there's so many ethical issues, regulatory issues associated with gene therapy. We cannot be modulating gene expression levels by putting in genes or by blocking genes, either using RNAi, or now we have better technologies like CRISPR-Cas9. Now, last week we had another paper on the CRISPR version 2, where we are talking of not gene editing mechanisms, but gene modulating mechanisms. So all of these things are coming. But from a clinical point of view, it's not very easy to take all of those things to the clinic because of ethical issues or regulatory issues. So the better way and the way forward for us as well as for the pharmaceutical companies to look at this as a screening mechanism for looking at other molecules where we can achieve that. So that is something that I'll leave that thought to you. Next slide, please. So this is our small group. We started 4 years ago, led by Professor Bishitas, who's a former director of our Institute of Cytology and Preventive Oncology, that in ICMR Institute. He was the founder director for that. Then also I went ahead to lead the Ambedkar Center for Biomedical Research at University of Delhi, and now he's with us. And he and I were the ones who actually started this institute, and then we've been joined by other people with different expertise. Next slide, please. This is the last slide. This is our campus, the smallest campus of AMITY University in Noida, just across the border from Delhi. It's around 62 acres. We have other campuses in Jaipur and Gurgaon, and we also have campuses now in Kolkata and Mumbai. So I invite you all to please come, be our guests, spend some time with us, and help us in our endeavor to use stem cells and tissue engineering for human health. Thank you very much.